What other distance measures do we know of? Sabine.
So the one thing that I know is the Hamming distance.
Okay.
That I think it refers to the number of different bits that these vector representations may have.
Okay.
And another thing that came to my mind that we use in vector databases as well is the cosine similarity,
Okay.
which we just measure the cosine of the angle between those two vectors that we have.
Mm-hmm.
These are two ways that.
Right. So if the Hamming distance is a distance that operates on a binary space, right, not a Euclidean space. So the distance, for instance, between these two samples is how much? 2. Excellent. And we also have the cosine similarity, or the cosine dissimilarity, or the cosine distance. It's really the same thing. Is to say if I have two vectors, right? In this case, I had a vector that was 0, 1, and then another one which was a 2, 1. Then I have two vectors like this. What is the angle between these two?
Exactly.
And based on the angle and based on whether they're pointing in the same direction or not, then we can define similarity or dissimilarity. Excellent. Right. So we have things like cosine similarity. We have things like LP norms. Yes, Manavjit?
Like we have Manhattan distance as well.
Right. So what is the Manhattan distance?
So
It's not the
because
distance that Parsa takes to work every day, by the way. That's something else.
yes. So I had it, like I studied it in like my first semester for a course, so I don't remember exactly. But the idea is, uh, if like it's like moving in a city, so like it is a grid based system. Like you can only walk horizontally or vertically, and not really how the Euclidean distance is like the straight line between 2 points. It's just the way you navigate between 2 points.
Excellent. Yes, absolutely. And we'll come to that in the next slide. So other types of distances include things like cosine similarity and maybe the general class of LP norms, which the Manhattan distance and Euclidean distance are one instance of, right? So what does that mean? Let's define the LP as or the LP norm is defined as such. Oops, not that. Highlighter out. We can define the LP norm as this. As a reminder, the last slide said something like for Euclidean norm, it was a distance from 1 to the number of dimensions that I have for xa minus xb squared at that particular dimension, right? That was the L2 norm, or the Euclidean distance that we defined, and now we're going to define the LP norm as this expression here. So for p equals 1, what does that reduce to? This would be equal to x1 is the sum from I to n of xi. Just the sum of the absolute values of a vector or of the vector of differences between two vectors. And what do we call this, Manavjit?
Sorry, I couldn't hear you. Like
I was saying that what do we call this particular norm? The L1 norm is what you mentioned earlier.
I think Manhattan distance is called N1.
Right, Manhattan distance. And why is that? Manavjit already gave us a bit of intuition. Let's say I have, a grid. These correspond to different, streets in a city. And I want to go from, one point to another point. I can't, well, I can't, maybe you can, but we can't really travel through buildings. So what we have to do is we need to take it street by street. And it turns out that this is equal to, this is the x1 dimension absolute value, and this is the x2 dimension absolute value. So we sum that up, and that becomes Manhattan distance. And it's called Manhattan or taxi cab distance because that's how taxis drive in Manhattan. Okay, so what about for 2 norm? 2 norm we've already studied. It's just the Euclidean norm. And as p goes to infinity, we have something called the maximum norm. What is the maximum norm? The name is already giving us the answer. What does it mean for maximum norm? So if I have a vector that is something like 1, 3, 15, and 2, -2, what is the L infinity of this vector? Yes, Sepideh?
I think so. We should calculate the max. I mean, the maximum is here 15.
Right. So in this case, this would equal 15.
Yeah.
If you plug infinity into here, you'll see that this summation would be overwhelmed by the maximum value because you're summing up each of the values to the power of infinity. And of course, whichever one grows fastest, whichever one with the highest base will outweigh everything else. And so that's what maximum norm is. Yes, Hamza.
Yeah, so just for, maybe it's a typo, but like for the maximum norm, you should also take the absolute value, right? Like if you have
Is it the
a
maximum
negative-
of, yes, you're absolutely right. It's the maximum of the absolute values of these instances. Right, because the absolute value is here. Yes, Mohammed.
What's the application of this maximum norm? I kind of get the P1 and P2, but the P of infinity, I mean, what's...
Someone give me a case where maximum norm would be important for us to understand. That's a good question. Where would we want to use maximum norm? So one example is, let's say that you are, you have a feature that represents, you have a vector that represents the coordinates of a particular robot within some environment. And you understand the boundaries of this environment, right? You know that it shouldn't exceed this wall, or shouldn't hit that boundary, or whatever. So one thing you could include in your optimization is the maximum norm should not exceed whatever threshold that you have.
I see.
And I think that also illustrates the point that we need not only use one distance, right? Earlier in the lecture, we talked about how distance defines our space, defines similarity and dissimilarity between instances, but you could have various constraints that represent your environment. You could have an agent that shouldn't exceed a particular threshold on any of the dimensions, while at the same time you want to minimize the Euclidean distance or the Manhattan distance for that agent to reach its particular objective, right? So you could use various ones within to define your system. Okay, good. So let's gain some visual intuition of LP norms. We're going to say in 2 dimensions, we want to identify and plot coordinates x1 and x2 that satisfy the constraint L1 is equal to 1. So that would look like, if I have coordinates, then let's start with the easy cases. L1 is, what was it again? It was just the sum over absolute values of my dimensions, right? That would be the definition of L1. And I want to set this equal to 1. So if this is x1 and this is x2, then that would be 1 point at the point 1, 0. Another point would be here at the point 0, 1. We have another one here. This is -1 and 0, and 0 and -1. And then everything in between. Make sense? So all the points on, all the points on this diamond are all points that have L1 is equal to 1. I see confused faces. Ask questions. Or maybe, I'm not sure. Okay. What about L2? You could draw out L2 in a similar way to save you a bit of time. This is what L1 looks like. What was the L2 norm? The L2 norm was x1 squared plus x2 squared square root. This has to equal to 1. For anyone who remembers high school geometry knows that this is the equation of a circle. And so L2 equals 1 or something like that. And you can, of course, continue this up until a very large number, tending towards infinity, and then you get, just the maximum value of a particular point. We need not visualize this in 2D, or sorry, before actually visualizing in 3D. We can have this for different values, right? Here we're saying that we have our LP is equal to 1. Our LP is equal to 1, but you could also plot it for some other value. Just gaining some visual understanding of what these LP norms are, right? And again, we need not just look at it in 2D, we can maybe look at it in 3D as well. It's the same thing. Now our diamond becomes this, what is it, an octahedron. And then the circle becomes a sphere, etc., etc. For those of you who are interested to learn more, maybe you can tackle the question on the bottom of the page, which is, can the P in LP take values smaller than 1? And would that still satisfy the definitions of a norm or a distance? Anyways. We also have, it was suggested to us to look at cosine similarity, right? Cosine similarity is really, it's in the name. It's the similarity between two vectors according to the distance defined as the angle between those two vectors. And if I have two vectors that are orthogonal to one another, then the cosine of 90 degrees is how much? Trigonometry. Cosine of 90 is 0. Someone said 0. Okay, excellent. So what does that mean? If I have a cosine similarity of, if I have an angle of 90 degrees and the cosine becomes 0, what does that tell me about the two vectors?
They are independent.
They're independent, meaning that none of them, no single vector gives information about another vector. That's what's meant in this case of dissimilarity. And sometimes we might have angles like this one here that the cosine is quite close to -1. And that means that they're anti-direction. They give negative, not that they give negative information about one another, but they're actually very much aligned, just in completely different directions. Again, depending on the problem at hand and the definition that you have about similarity and dissimilarity and distance, that's how you would go about solving your problem. Shima.
Yeah, actually, you just answered my question. I wanted to know that
Excellent.
which one is worse.
We'll see an example of when you'd want to use this over the other ones in a couple slides. Okay, so to summarize then, cosine similarity looks at the angle between two vectors, whereas Euclidean similarity or LP similarity looks at the distance between two vectors or 2 points. When would you want to use cosine similarity over Euclidean distance? Let's look at an example. Let's say you are Amazon, you're an e-commerce website, and you want to compare users for product recommendations. You have 3 different users. User 1 has bought 1 egg, let's say egg, 1 flour, and 1 egg sugar. User 2 has done the same thing, just 100 times more. And user 3 has bought 1 egg, 1 vodka, and 1 Red Bull. They have a party going on. So who is similar to whom based on which metric? Let's say we have a Euclidean distance. Which users would be similar to one another? Shima.
1 and 2 based on the features. Based on the
Okay, so
type of
let's draw this out. Let's say how many unique dimensions do I have? 1, 2, 3, 4, and 5, right? So let's say that user 1 is 1, 1, 1, 0, 0 in terms of what they purchased. That's user 1. User 2 is 100, 100, 100, and 0, 0. Yes. And user 3 is 1, 0, 0, 1, 1. Right? We've now just took that information and put it in vectors. So based on Euclidean distance, which users are similar to one another? Shima, which did you say?
actually based on a Euclidean distance, the answer will be different.
Okay, it's 1
The
and
number, yes, 1 and 3, for
1 and 3.
example.
And based on cosine similarity,
1
yes,
and 2.
1 and 2. Now, which one is correct? Which similarity do we use?
Cosine.
Fine.
It depends, right? If you're trying to classify, them based on maybe how much weekly budget they have, then maybe you want 1 and 3 to be similar to one another. But if you want to recognize who's having a party and who's not, then maybe you want to use the other way around, Euclidean versus cosine. right? So your definition of distance is something that's, you know, it's decided based upon the domain and the problem in which you're trying to solve. And it determines everything downstream, like we said, in the case of a Swiss roll. You care about local geometry. You care about local geometry, or sorry, local versus global geometry. So everything downstream of your definition of distance is going to define how your problem is going to be solved. Guru, is that still a question? Your hand is up. No? Excellent. So any questions then? I hope that we now have, I'm sure we do, an appreciation for definitions of distance and a bit of mental intuition about how they look like. Okay, so by cosine similarity, users 1 and 2 are more similar. And by Euclidean similarity, users 3 is more similar to user 1.